decided to simulate a quantum computer. It got interesting fast. And to understand why, I had to go back to the basics. Here is a Bloch sphere that I created in Three.js. I will give a brief description of how the Bloch sphere can represent the state's superposition. So, in the classical sense of computers, you can think of it as if it was a switch where there's only the values on and off. But in the quantum sense, it's not strictly on or off. Instead, it is a probability of on and off at the same time. It's like a coin being spun in the moment. It's not exactly head or tails, but both at the same time, kind of, with a probability. Anyways, if we just transform the state on this Bloch sphere with a Hadamard gate, it will go on the x-axis and leaving the pole, turning into a superposition. I'm not going to go much into detail here, but as you can see here, every distinct rotation simulates a quantum gate, physically showing how we manipulate quantum probabilities. Now I need to find a way to represent multiple qubits together. First, I represented the group qubits as a struct, a way for it to exist, and then a way for it to take in multiple qubits. The Kronecker product can be used to combine both the old state and the new state. We could also think the formula like this, where A and B is part of vector R, and C and D is part of vector N. Do the formula and you will get something like this. Now, to implement the gates. But first we need to know how we should do it. We're gonna have to loop through every single state, usually as I for the index. Then view I as a binary number, flip one bit of I, see if I is less than j, then confirm the operation. Since I is less than j, we just handle this pair once. In this case, for x gate, we just swap the amplitudes. Now let's implement that logic. The x gate, the Hadamard gate, and the control NOT gate. Now let's test them and see the results. By the way, this is my first video, so please support me. Anyways, as you guys can see here, you can see that it matches the matrices on the right. I don't know about you, but it seems pretty cool to me. But anyways, moving on. Usually we're taught that a qubit holds the amplitudes on its own right, like independently. That's actually wrong. In this simulation, we can prove it. So I first created a register and initialized it. Push two cat zeros into the register. Applied the Hadamard gate on qubit number 1. Then applied the control NOT gate with the control index being 1 and the target index being 0. Then we output the new state as a result. And this is what we get. What this means is when we measure both qubits, we only ever get two results. Both are 0 or both are 1, nothing mixed. So this proves that when the two qubits are measured, they will always match each other. Measuring is just an amplitude squared, so if we do that, we're going to get 1/2. And we did. So when you measure them, you don't get independent randomness anymore. Each qubit is random on its own, but the results are perfectly correlated, as if they share the same pattern. If there's anything else you want to see this quantum computer do, let me know. Bye.